Try this problem. Now let's discuss the solution. First, we have to choose a problem-solving framework. Early in your class, kinematics and projectile motion might be the only problem-solving framework you've seen so far. And this problem is projectile motion because after the package is released, but before it hits the ground, there will be nothing touching the package. So during that interval, the only force on the package will be the force of the Earth's gravity. So during that interval, the package will be experiencing projectile motion. So we'll use our systematic method for projectile motion. We've already completed this step. We should check for SI units. Now, because this is a symbolic problem, there were no units given. So we don't need to really, there's no units to check. Now, because this is a symbolic problem, we need to identify the given symbols. The given symbols are the symbols generally that are mentioned in the problem. So, for example, this problem mentions this symbol lowercase v. Therefore, we're going to treat that symbol as a given. That is, even though we don't actually know a number for little v, we're going to act as though we had a number for little v. We'll use this symbol as though it represents a number that we know. And then similarly, the problem mentions the symbol capital D. So we can treat that symbol capital D as a given. Now, there is an exception to that. The problem also mentions little h, but obviously that's not a given. Little h is mentioned, but obviously that's not a given because that's what the question is asking us to determine. So I'm not going to write little h in the list of givens. And there's one more exception. Something else we can treat as a given is little g, the magnitude of the acceleration due to gravity. Now, clearly little g was not explicitly mentioned in the problem, but the rules of the game in physics problems is that we can treat physical constants as given. Since little g stands for a physical constant, we treat it as a given, even though it's not mentioned in the problem. Who cares? What does it matter what the givens are? Well, there's a couple of reasons, but one reason is that we have to make sure that our final answer includes only these symbols. Our final answer should include only the symbols that are given in the problem. If your final answer includes any symbols that are not given in the problem, that would usually be considered incorrect. So we're allowed to use all of these symbols in our answer, including little g, even though it was not mentioned specifically in the problem, because we're allowed to use constants. So here's a summary of these rules that we were just discussing. Any symbol that is explicitly mentioned in a problem is treated as a given. So since little v and capital D were explicitly mentioned, those are treated as givens. Any symbol that is not explicitly mentioned in the problem is not treated as a given. And only the givens should be included in our final answer. But remember, there are a couple of exceptions. The symbol that represents what the question is asking you to determine is obviously not treated as a given. So we're not going to treat little h as a given because that's what the question is asking us for. And the other exception, we should treat little g as a given, even though it was not specifically mentioned, because it represents a physical constant. And again, one reason why this is important is that these are the symbols that we are allowed to include in our final answer. I recommend that you don't just identify them in your head. I recommend you actually write down the given symbols. Write down the given symbols. Now we'll move to our next step of drawing the sketch. Remember that our sketch here is going to be a parabola. So let's draw that sketch. Okay, so here's the path of the object. Now, the key to drawing this path is to pick up on the key word in the problem that the plane is flying horizontally. That means that the initial velocity of the package is horizontal. But remember, the velocity should be tangent to the curve. So if the initial velocity is horizontal, then the curve must have a horizontal tangent at the initial point. So I tried to draw that here. Basically what that means is that we're drawing the right half of a parabola from the peak and to the right. Let's see. Well, besides the path in that sketch, we should also build any given information into our sketch. Now the problem already built this distance h into the sketch, but we can also build this distance d into the sketch. So I'm assuming that this point here is the point where the package is released for simplicity. So this distance d is what they're mentioning in the problem. Remember that in physics, capital letters and lowercase letters matter. This is a lowercase h, but this is a capital D. Try to be consistent with that. And remember, whenever you mark any distance, you should mark where it begins and where it ends. We should also try to build the question into the diagram, and they're asking for the height h. So we should build that into our sketch with a question mark. Okay, so we drew the sketch with the path. The path in this case was the right half of a parabola, starting from the peak of the parabola. We built some distance information into the sketch, and we also built the question into the sketch with a question mark. Now our next step is to indicate the key points in time. The two key points in time in this problem are this point where the projectile motion begins, which I can call t sub 0, and this point where the projectile motion ends, which we could call t sub 1. This is a key point because the question asks us about the distance to that point. And this is a key point because we were given information about that point. Remember, we're treating this symbol as a given, as if we knew this number. So according to those rules, we were given information about that point. Those are the only key points in time for this problem. Next, we should write down our axes. So we'll stick to our standard axes of up and to the right for projectile motion. Next, we'll write down our origin in the standard position, the lower left corner. So we do not put the origin here. We put the origin here in our lower left corner. So at that point, the coordinates for position will be 0, 0. We've completed this step. Now we're going to label the coordinates for position at our key points in time. So here the coordinates will be x0 and y0. So x0 has a coordinate of 0 because it's at the same horizontal position as the origin. And vertically, we're at a distance of h above the origin. So here are those coordinates. And then here, the key coordinates would be labeled x1 and y1. Always try to use the exact right symbol with the exact right subscript. So the horizontal coordinate here is d, because this is at a horizontal of distance of d from the origin. And this point has the same vertical location as the origin. So the vertical coordinate will be 0. So here I'm trying to write a capital D as best I can. So notice that for this symbolic problem, we were unable to write numbers for some of the variables. We could write some zeros, but otherwise we couldn't write numbers. But that doesn't mean you shouldn't write anything. For a symbolic problem, if you can't write a number, don't just give up. Instead, write the symbol that you were given in the problem. So we were able to write appropriate symbols for y sub 0 and x sub 1. That's what I meant here in the handout when I said that when you label the coordinates, you should include a specific value, or if not a value, you should include a specific symbol. Here we included a specific symbol for the coordinates when possible. To be precise, we included the specific symbol h for y sub 0 and capital D for x sub 1. Now we're ready for our next step, which is to break the starting velocity into components. Now it's good to begin by drawing the initial velocity in our main sketch. How would you draw that? Well, we've already discussed that. The initial velocity here will be horizontal. And I've already drawn the path so that I can draw the initial velocity here tangent to the path and have the initial velocity be horizontal. So let's draw that in. Here I've drawn the initial velocity horizontal, tangent to the path at this point. You should always label every vector. So the general symbol we would use for this vector is v sub 0 for the initial velocity, or the magnitude of the original velocity. And on this particular problem, the specific symbol for that initial velocity is just lowercase v with no subscript. So here's how I can label this initial velocity with a general symbol and a specific symbol for the magnitude. All right, so again, we're showing what it means to, this is horizontal. Let's talk about that a little bit more. This is supposed to represent the initial velocity of the package. But the problem doesn't talk about the package here, it's talking about the plane. So is this really correct? Well, yes it is, and here's why. The plane is flying horizontally. That means that before the package is released, while the package is in the plane, the package is also flying horizontally with a constant speed of v. And that means that at the instant that the package is released, at the very instant at the beginning of the projectile motion, that package is still moving horizontally with speed v. Now, immediately after that instant, the velocity will start changing as gravity curves the path downwards. But at the instant the package is released, it'll still be moving at the same speed and direction as the plane was. So it is correct to apply this information about the plane to the initial velocity of the package. And that's a thought process that you'll often need to use on projectile motion problems when one object is released from another. Now, we still need, that's just the start, we still need to break this vector into components. So let's go ahead and try to break that vector into components. So here's the vector. So the magnitude of the overall vector is v. And now we need to write down the x and y components. Well, because the initial velocity is horizontal, there is 0 vertical component. Because the initial velocity is horizontal, there is 0 vertical component. And for the same reason, the entire magnitude of the, and now let's do the x component. First of all, remember you should always do the sign of the component first. Well, this component, well, this velocity is pointing to the right, which is our positive direction. So I'll start by putting in a plus sign here to show that the x component is positive. And because there's no vertical component, the magnitude of the x component is the same as the overall magnitude. We take the entire magnitude of the original vector and put it into the x component. And one more thing that we should fix here, as we've talked about many times in the previous videos, in projectile motion, the x component is constant. So we should not include time subscripts for the x component. So I can simply say that this is going to be the x component of the motion for the entire projectile motion. Okay, so that's how we break a horizontal vector into components. Do you understand the difference between these? So these are our general symbols that we would use on any problem. These are the specific symbols we're using for this problem. This is the overall magnitude of the original velocity. This is the x component of the velocity throughout the projectile motion, and this is the y component, the initial y component of the velocity. So here's a summary of some of these new ideas that we were discussing here. If the initial velocity at the beginning of the projectile motion is horizontal, as in this problem, then the path of motion begins at the peak of a parabola, where the tangent to the parabola is horizontal, as we drew here. So look for a clue word like the word horizontal here. And we also saw that when a vector is parallel to the x-axis, then the y component is 0, the x component is positive, and the entire magnitude of the vector goes into the x component. So we've completed this step. We broke the starting velocity into components. Now notice that on this problem, I would say that we were given the starting velocity. This problem does give us the starting velocity. Of course, it doesn't give us a number, but remember it gives us a symbol, which we're going to treat as a given. So we were given, in a sense, the starting velocity. So we don't want to skip this step, even for a horizontal starting velocity. Moving on, we need to label the initial and final positions on our path. I'll choose this as the initial position and this as the final position. Those are the 2 points we care about. We care about this point because the question is asking about it, and we care about this point because we were given information about it. Now we're ready to write down our setup for solving the problem. Here's the setup, so let's write that down. Now, what should I plug in for a sub y? On previous problems, we plugged in negative 9.8 meters per second squared, but because this problem is symbolic rather than numeric, to be consistent, we should plug in a symbol for a sub y rather than a number. So what is the correct symbol? Is this the correct symbol? Is this what we should plug in for a sub y? No, this is wrong. And here's why. Because what does little g stand for? What does little g stand for? Well, I hope nobody said little g stands for gravity. Well, did you come up with the correct answer? Little g stands for the magnitude of the acceleration due to gravity. Okay, now because it's a magnitude, little g does not include the correct sign. Remember, a sub y is a component, and components need signs. The acceleration, gravity is a downward force, so gravity will cause objects to accelerate downwards, and downwards is our negative direction. So we must include a negative sign on the g here. We must include a negative sign on the g. It's not included inside of the g, so to speak. We have to put it in separately. The g by itself is just the magnitude. That is, g stands for 9.8. G stands for 9.8 meters per second squared, the magnitude of the acceleration due to gravity. G does not include the negative sign. We have to put that in ourselves. Now remember that the reason that this acceleration is negative is because it's the acceleration due to gravity. And the acceleration due to gravity is downward, and we've chosen downward as our negative direction according to these axes. Now, of course, if we had chosen different axes, if we had chosen downward as our positive direction, well then of course this acceleration would be positive. And in fact, some students might prefer to choose downward as the positive direction on a problem like this, where the object is moving only downwards and never upwards. That would be a perfectly fine way to solve the problem. But I don't think that's the method that's used in most textbooks, and I don't think it's probably the best method for beginners that are having difficulty with projectile motion. If you find these problems to be challenging, I think it's best to stick with the method in these videos, which is always choose up as your positive direction for projectile motion problems. So if you follow that advice, and if you choose up as your positive direction for projectile motion, then in that case you have to plug in negative g for a sub y when you're doing symbolic problems, as we have discussed. We've completed this step. Now we're ready for this step. In our setup, we want to indicate the question. Well, we've already noticed the question was asking us for h, and we've seen that h here will represent the initial vertical coordinate. When we know the initial vertical coordinate, we'll have the answer to the question. So I'll put a question mark here to show that this is what the question is asking us for, and then I'll write down the specific symbol we're going to be using for that in this problem. So we indicated the question not just with a question mark, but also with the specific symbol that we're trying to solve for in this problem, which was h. Moving on to the next step, we want to write down symbols for each variable using the work we've done previously. So x final will be capital D. X initial will be 0. Vx will be what we figured out here, V. I'll leave out the extra plus sign now that I'm plugging into the equation to make the math simpler. Delta t, we don't know, so I'll simply write down the symbol delta t for that. And again, we don't know what delta t is over here, so I'll leave that blank for the time being. Y final is 0. V initial y is 0. Now this right here is one of the keys to solving the problem. Notice that this number was not given explicitly in the problem, so a lot of students don't come up with this number. Notice that this was implied though when they say the plane was flying horizontally. Since the plane was flying horizontally, the initial velocity of the package was horizontal, and that meant that the initial vertical velocity was 0. So this was a hidden 0 that was implied but not stated in the problem, and it's important for solving this question. By the way, notice that the plane is flying with constant speed, but that doesn't mean that the package has constant speed. Once the package is released, the package's speed will be changing because of gravity. So the initial vertical velocity is going to be changing to a different final vertical velocity. The plane is moving with constant speed, but not the package. The package has constant horizontal speed, because that's always true for projectile motion, but the package does not have constant vertical speed. And we don't know what v final y is. So again, I'll leave that blank. Now, this is the concept that we'd like to figure out. But so far, we only know values or symbols for 3 of these. So we're not yet ready to pick a y equation, because remember, you need 4 to know 4 y variables to choose a y equation. But how about here on the x side? Well, remember that d is a given, and v is a given, so that means there's only one unknown in this equation. And when an equation has only one unknown, you can solve the equation for the unknown. And now maybe you can see why it was useful to write down the givens. It's useful to write down the givens on a symbolic question because that way you don't confuse the given symbols with the unknown symbols. If you know which symbols are given, then you can more easily count how many symbols in each equation are unknown, and that gives you a better sense for when you're ready to solve the equation. Okay, so since 2 of these symbols are given and only 1 is unknown, we should start with the x component and solve the x equation. What are we going to solve the x equation for? For the unknown, delta t. I'll simplify a bit. Now we can remember delta t is the unknown. So to get delta t by itself, we need to divide both sides by v. And now we've solved for delta t. And then we can take this value and put it in up here. Now notice that we have 4 concepts that we know now for the y equation. We know this, 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 and this. And when you know 4 y variables, you're ready to pick a y equation. Of course, we don't know this. Now, why do I say that we know this? Well, we know it in the sense that it uses only the given variables. delta t here, now we have an expression using only the given variables. And remember, the rules are that we pretend that we actually know the values for the given variables, even though we don't. So we're going to pretend that we actually know the value for delta t. We have an expression for it in terms of the given variables. And of course, we can treat g as a given, as we discussed earlier. So given that there's 4 things that we know, so to speak, we're ready to pick a y equation for h, which we don't know. Remember, h is not in our list of givens. Well, as is usually often the case, the variable we don't care about here is v final y. So we'll pick the normal equation that we pick when we don't care about v final y, which is our standard projectile motion equation. Then we can plug in from our framework. Y final is 0, y initial is h, v initial y is 0. And here again is where a lot of students would get stuck on this problem. Many students don't realize that they should plug in a 0 here, because remember, this 0 wasn't given specifically in the problem. We inferred that this was 0 because the plane was flying horizontally. That's one of the keys to solving the problem. Remember to plug in negative g for a sub y, including the negative sign. Now, I hope you can see that this would be wrong. Can you see that this would be wrong? This is wrong because this would imply that we're only squaring the d. But you can see from, but what we want to do is square the entire expression that represents delta t. So you need to have enough mathematical sophistication here to put in parentheses. You need to put in your own parentheses here to show that we're squaring the entire expression that represents delta t, not just the numerator. So those parentheses are important. This term is 0, so that term disappears. Adding a negative is like a subtraction. So we'll turn that into a subtraction. This term is gone because it's 0. Now, here's where you might get confused because there's all these symbols here, but remember, these are all givens. What we're trying to solve for is h. It helps to have indicated the question with a question mark, so we need to solve that for h. Remember, h is what we were trying to figure out, so it appears we're about done with the problem. So we've completed this step. We started by knowing 3 of the 4 x variables, so we could solve the x equation. We knew this, and this. We knew them in the sense that either we had a number or we had a given symbol for those. So we were able to solve this for delta t. And then at that point, we knew values for 4 y variables. When I say we knew values, what that really means is that we knew a value or an expression in terms of given symbols for 4 of the y variables. So we were able to choose the equation and solve. In this case, we didn't need the quadratic equation. We didn't need the quadratic equation because the unknown that we didn't know was not being squared in this case, so we could solve without the quadratic equation. Now I think we're ready to state our answer to the question. And we want to make a series of checks. Did we really answer the right question? Well, yes, we figured out the height above ground that the plane was flying. Did we answer all parts of the question? Yes, this was a single part question. Now, we should check, well, let's first check that this idea. Let's check that our answer includes only the givens. Actually, let's look at this first. Notice that on this problem, we should not include units because this is a symbolic answer. So I don't know whether most graders would actually take off points for this. Probably most graders would not take off points. But still, it's not really correct to include meters here. You really shouldn't include. SI units for height are meters, but you really should not include those separately here. And the reason is that all the units are thought of as included in the variables. So for a symbolic answer, do not include units. For a symbolic answer, do not include units. Is the best practice. For numerical answers, you should include units. For symbolic answers, as on this problem, don't include units. Instead, what you should do is check that your answer includes only the symbols treated as givens. Well, remember, these were the symbols that we identified as givens. So little g we're allowed to use because that's a given. Capital D we're allowed to use because that's a given. Little v we're allowed to use because that's a given. Remember to try to use the correct uppercase and lowercase when you're writing your answer. So we only included the givens. Of course, h was not a given, but it's okay to write the h over here on the left side of the answer. What I mean is that we should only include the given symbols over here on the right side of the answer, where we actually write out an expression for the answer. So that's good. So let me show you how we could have gotten this wrong. Suppose, did I make a mistake here? Yeah, I did. Oops. Square should go here, shouldn't it? The square goes over here. Again, it would be wrong if we leave out the parentheses. We have to include these parentheses here to show that this entire expression, not just the numerator, is being squared. So when I had the square here and that was a mistake, this is the correct way to write that. All right, so here's our answer. And let's see, where were we? Oh, so let me show you a wrong way to write this. Here's a way that some students might end up writing this. Now, this would be marked as wrong, even though in a sense it's right. After all, d over v is delta t. d over v is delta t. So in a sense, this is right, but the grader would mark it as wrong because it's using a symbol that was not given. We're not allowed to use delta t in our answer. We're not allowed to use delta t in our answer because that was not one of the given symbols. So even though, in a sense, this is on the right track, it's not a correct final answer. This would be an acceptable intermediate step. This is an acceptable intermediate step, but it's not acceptable as a final answer. So it's wrong as a final answer, even though it would be an acceptable intermediate step. We have to use d and v in our answer because those are the given symbols. We can't use delta t in our answer, even though it's the same as d over v, because that was not a given symbol. So hopefully now you understand better what I meant when I said only symbols that are treated as givens should be included in our answer. So for example, on this problem, we should not include delta t in our answer because that's not a symbol that we're treating as a given, because that's not a symbol that was explicitly mentioned early on in the question. Okay, so we did check that our answer included only the given symbols. We did that correctly. We should also check that our answer makes sense. How can we check whether this symbolic answer makes sense? Well, as I've talked about on previous videos, you should always check whether your answer is positive or negative and whether that makes sense. So is this positive or negative? Well, if you think about it, all of these symbols are positive. G is positive because it stands for a magnitude. D is positive because it stands for a distance. And v is also positive because it also stands for a magnitude, the magnitude of the initial velocity. So since all those symbols are positive, this answer came out positive. Our math told us that h is positive. And that makes sense. It makes sense that h should be positive. So suppose that h had come out to be negative. If the math had told us that h comes out to be negative, we would have known we made a mistake somewhere along the way. It wouldn't make sense for h to be negative on this problem. So if we happened to have gotten a negative h, that would have meant some kind of math or setup mistake somewhere in the problem. So you should be able to tell that this would be a wrong answer. Now, is there anything else we can do to check whether this answer makes sense? Well, in the past, I've told you with numerical answers that you should check whether the size of the answer makes sense. But we can't really do that with a symbolic answer. But there's something else we can do with a symbolic answer to check whether this symbolic answer makes sense. Imagine that we increase d and hold all the other variables constant. If we increase d and hold all the other variables constant, what does the math of our answer imply will happen to h? Imagine increasing d, holding all the other givens constant. What would the math imply would happen to h? Would h increase or decrease? Well, notice that d is on the top of this fraction. So if we increase d, we'll make the top of the fraction bigger, which will make the whole fraction bigger, which will make this whole expression bigger, which will make h bigger. So I hope it's apparent to you that the math here implies that if we increase d, h will also get bigger. That's a correct implication because, again, we're imagining that we're holding the other givens constant, and because we know that all of these variables are positive, which makes it easier to interpret the math. Now that we know what's mathematically implied by our answer, well, let's actually ask what's mathematically implied about v. Suppose that we imagine increasing v in this answer. Mathematically, if we hold the other givens constant, would that cause h to increase or decrease? Well, notice that v is on the bottom of this fraction. I hope you know that if you make the bottom of the fraction bigger, that makes the entire fraction smaller. And that would make the whole right-hand side smaller, which would make h smaller. It should make sense to you that since d is on top of the fraction and v is on the bottom, increasing d has an opposite effect on h as increasing v. d is on the top, which means increasing d increases h, and v is on the bottom of the fraction, which means increasing v decreases h. The bigger the denominator gets, the bigger the bottom of the fraction gets, the smaller the entire fraction gets. I hope you're familiar with that idea. So this is what's mathematically implied by our answer. Now we have one more given to consider. Besides v and d, there's also little g. So we should also ask, if we increase little g, what will happen to h as mathematically implied by our answer? Again, maybe you should pause the video and come up with an answer. Well, this should be straightforward. If we increase g, that's going to increase the right side of the equation, which means that h has to increase the left side of the equation. You could think to yourself that g is basically a numerator, and when we make this top of the fraction bigger, the whole fraction gets bigger, and that means the whole right-hand side gets bigger, which means h gets bigger. So this is what's mathematically implied by our answer, but now we need to check whether our answer makes sense. Now when we ask what makes sense, we don't want to think about what's implied by our answer, so maybe I'll push the answer off the screen here. And now let's ask again, suppose that we increase d and hold the other two givens constant, what would we expect to happen to h? What would make sense intuitively would happen to h? And again, you should pause the video and think about that. In fact, you can think about each of these three. How would each of these three affect h? Well, let's start with increasing d. So if we increase d, remember that we're imagining holding v constant. And remember, v gives us our horizontal speed. So if we increase the horizontal distance, but go at the same horizontal speed, doesn't that mean it'll take more time? So that's the first step of the analysis. If we want to travel a greater horizontal distance with the same horizontal speed, it'll take more time. But in order for the fall to take more time, doesn't it have to start from a greater height? If we want the fall to take more time, it has to start from a greater height. If we keep driving off the same height as before, or actually in this case, I guess I forgot where the package is being released from a plane. So if we, so I should say here that if we want the package's fall to take a greater time, the package has to be falling from a greater height. We want the package to go a greater horizontal distance with the same horizontal speed. So it has to be falling for more time, so it has to be dropped from a greater height. Now, it helps here to realize that our analysis over here was based on the x component. Here we are imagining a greater distance in the x component, which will require more time to complete. And then this part of the analysis was based on the y component. If we want the package to be falling for a greater time, it has to fall from a greater vertical height. And we see that, as usual, the link between our x component and our y component is the time that elapses. And now if you notice, what makes sense also matches what was implied by our answer. So that's a confirmation that this answer was correct. Now let's check what would make sense if we increase little v. Now remember that on this problem, v was the initial speed, which gave us the constant horizontal speed of the package. V gave us the constant horizontal speed of the package. So what would happen, what would make sense if the package was released with a greater horizontal speed? Well, remember now we're imagining holding the other two givens constant. Well, if we want to have a greater horizontal speed, but travel the same horizontal distance, that's going to take us less time. If now the package is being released with a greater horizontal speed, but it's still accomplishing the same horizontal distance, that's going to take it less time. And if we want the package to be falling for less time, it has to fall from a lower height. In order to be falling for less time, the package has to be falling from a lower height. So an increase in v should decrease h. And notice here, again, we started by analyzing the x component. We started by analyzing the x component because v gave us the horizontal speed. But then we moved on to analyze the y component. Because h represents a vertical distance in the y component. So we see that v and h should be inversely related, move in opposite directions, and that's the same thing that was mathematically implied by our answer. So again, we have a confirmation that our answer was correct. Now finally, what would make sense if we increase little g? Now, how can you increase little g? Isn't little g a constant? Well, I talked about this in the previous video. You could imagine moving to another planet with stronger gravity. If we move to another planet with stronger gravity, how would that affect h? I think this analysis is more challenging than in the previous case. There's a couple ways to think about it, but here's one way you can think about it. So suppose you move to a planet with stronger gravity. Doesn't it make sense that if there was stronger gravity, we would expect the path to look more like this? That with stronger gravity, the path would curve down more quickly and the package would hit the ground sooner. So notice that with stronger gravity, we would tend to expect to cover a smaller d. Stronger gravity would tend to give us less distance. But remember, that's not allowed. In our little experiment here, we're imagining increasing gravity while increasing the acceleration due to gravity while keeping d constant. So we can say that if we increased little g, that would tend to decrease the horizontal distance. I think that makes sense. If we tried this experiment on a planet with stronger gravity and a stronger acceleration due to gravity, that would tend to decrease the horizontal distance that the package covers before it hits the ground. But remember, in our we want to imagine that we're holding d constant. So we have to ask, how would h have to respond to hold a d constant? And I think it would make sense that h needs to increase to keep d constant. If little g increased and there was no change in h, that would decrease the horizontal distance. If we just had stronger gravity, that would decrease the horizontal distance the package flies. So in order to keep this given constant, we also need to release the package from a greater height. Notice that if we release it from a greater height, then even with stronger gravity, if we released the package from a greater height, then even with stronger gravity, it might still travel the same horizontal distance as before. That's one way to work it out. So according to our logic, if we increase the acceleration due to gravity, the magnitude of the acceleration due to gravity, we will have to release the package from a greater height in order for it to travel the same horizontal distance as before. I think that was a more challenging analysis, but notice that that matches our result here. So we have that our answers make sense. What's the advantage of doing this? So like I discussed in the previous video, this is a difficult and can be a time-consuming process, but there's a couple of advantages. One thing is that it can help you to catch your mistakes. If we had made a mistake somewhere along the way and for some reason we had gotten this answer, it's very easy to get the bottom and the top of a fraction mixed up. If we had gotten the bottom and the top of this fraction mixed up, we should have been easily able to see that this was the wrong answer because it wouldn't make sense. This would mathematically imply patterns that wouldn't match our common sense. That would give us a chance to catch if we'd made a mistake. And the other advantage to trying to check whether your answer makes sense is that it's a very good way to simply build your understanding and intuition for the concepts. I know it's challenging to ask what makes sense, but the more you work at it, the better understanding and intuition you're going to get for the concepts. And as I mentioned in the previous video, if you find this difficult, you don't necessarily have to try to ask whether every single variable on a symbolic problem makes sense. You might just try to pick one or two of the easier variables to think about and ask if those make sense. And you can already get some benefits just from that. You might already, just by checking one or two variables, be able to catch some mistakes that you might have made on some problems. But the more you practice this skill, the better you'll get. Okay, so we did the checks, including checking for that our answers made sense. Okay, so what have we learned from this problem? One more thing here. Here I analyzed this in terms of components, but there's always multiple ways that you can analyze this. You could analyze this first pattern more simply by saying that if you want the package to cover a greater horizontal distance, it just matches common sense that you'd want to drop it from a greater height without actually thinking about delta t explicitly. You could just say if you wanted it to fly through the air for a greater horizontal distance, common sense would tell you it needs to be dropped from a greater height. So this is one way to work out what would make sense, but it's not the only possible way. So what were the important skills that we covered in this video? One thing we saw here was the importance of this word horizontally. The fact that the plane was flying horizontally meant that the initial velocity of the package was horizontal, and that told us that the initial vertical velocity was 0. That number 0 was very important for us to plug into our equations as we went along. Remember, you need to plug in negative g for a sub y, not just g. We saw how it was useful to have made a list of the symbols that we're treating as givens for the problem, using these rules for identifying the givens. and we practiced this difficult skill of trying to ask for a symbolic answer. If we change each of the givens while holding the other givens constant, how would we expect that to affect our answer? We checked what was mathematically implied by our answer and what would make sense. And that's a useful skill for you to keep practicing on your own for symbolic problems. Now you can move on to the next video and try the next projectile motions problem. And remember that there's, to accompany these videos, there's also a problems document that contains all the problems. If you don't have, my recommendation is that it's best to do all the problems in this series in order, because the order of the problems is chosen to aid your learning of the material.